Hi guys, in this chapter we're going to be covering various aspects of communication networks. These include traditional and higher speed networks. For instance, LANs are local area networks, like a network that would be set up at a college, for instance. And these different networks have different geographical regions, different maximum data rates, and these types of characteristics. So that's really what we're going to cover here. So as I mentioned, local area network is a LAN. A wide area network is a WAN. And then there are the traditional and more of the high-speed versions of each of those. So you can see we have high-speed LANs and then high-speed WANs. We also have the metropolitan area network, which is considered a higher speed network as well. So that's a MAN. Okay, so this chart is nice in the sense that it shows you the data rate in bits per second versus the distance in meters that one of these given networks would cover. So it's really the coverage area and the data rate that it can support. So if you want to get a feel for how traditional wide area networks are in terms of their characteristics, you can see these cover much larger distances greater than say 1,000 meters and upward. But the data rates that it can support are lower. So you can see like 10 to the 6 is like 1 megabit per second and lower. So by today's standards, we're coming up on 2020 here. So, by 2020 type of standards, it's definitely on the lower side. Now, a traditional LAN, something you'd see as far as coverage area on the order of, several hundred meters. Like a college campus would qualify as a local area network type of coverage area. And you typically have more concentrated use, so you would need to support, data rates that are higher than say 1 megabit per second, up to like 10 megabits per second. But then again, today we have more high-speed versions and flavors of these types of networks. So you can see high speed, you're getting up toward 100 megabits per second and higher. Similar with MANs, you're right here and upward, and the coverage area is on par with what a local area network would be. So then what's the highest data rate and highest coverage area and largest coverage area? You're talking your high speed WAN. So those are the types of things to look out for. And this is a great chart that kind of summarizes some of this stuff. And then there's a multiprocessor, which is on there as well. So we're going to dive a little deeper into the characteristics of each of these types of networks. So let's focus first on wide area networks. So it covers, on average, it's going to be the largest geographical coverage network. It also has the circuits that are provided as part of these networks are provided by a common carrier. So like a Verizon or AT&T, this type of common carrier type of network consists of interconnected switching nodes. Traditional wireless area networks provide modest or moderate capacity, as you saw from the previous chart. And then higher speed WANs. Why are they higher speed? Well, they communicate via optical fiber and light, essentially. And the transmission techniques that are used in these higher speed WANs is known as ATM, or asynchronous transfer mode. So this allows you to achieve the tens to hundreds of megabits per second. So let's shift over to LANs. So like a wireless area network, a local area network interconnects a variety of devices and provides a means for information exchange among them. Traditional LANs, as you saw from that chart, provide data rates on the order of 1 to 20 megabits per second, whereas the higher speed LANs can get up to from 100 megabits to 1 gigabit per second. So here's a simple graphic of a local area network. You have a shared transmission medium, and you have the various workstations that interface with that transmission medium to back to a server, and the server basically works in conjunction with the workstations to set up this simple LAN or local area network. So again, on a college campus, it's common to have a server room, and then have your computer labs, have your Wi-Fi access points, and then you can hook up your phone or your laptop to the Wi-Fi, and this is kind of the way that a LAN would be set up. So what are some key differences between LANs and WANs? Well, the scope of a LAN is typically smaller, as you saw, pictures worth 1,000 words, and the LAN interconnects devices within a single building or cluster building. So again, I always go back to the college campus example, perfect example of a LAN. A LAN usually is owned by the organization that owns the attached devices. So if it's the college campus, well, the college would typically own the attached devices. For WANs, most of the network assets are not owned by the same organization, which is a key differentiation. And the internal data rate of a LAN is typically greater, which is an important distinction. The need for MANs, so metropolitan area networks. So traditional point-to-point switch networks techniques used in wireless area networks are typically inadequate for growing the needs of organizations. So you need typically high capacity and low cost over a large area to really function in this domain effectively. So that's what a MAN gives you. It provides service to customers in metropolitan areas. It gives them the required capacity and data rates that are needed to serve the plethora of needs that are the demands really on the network, and it does this at a lower cost and a greater efficiency than the equivalent service from a telephone company. So that's really where you started to see the transition from those services that were provided previously by telephone companies toward these metropolitan area networks. All right, so we need to go over some switching terms. So some important definitions you need to know are the switching nodes themselves, the stations, and also the communications network. So just so we're on the same page with that. So for switching nodes, there are a switching node is just an intermediate switching device that moves the data around. Okay, you're not concerned with the content of the data at the switching node. All right, with stations, these are the end devices that wish to communicate. And then each station is connected to a switching node. And then the communication network itself is just a collection of switching nodes. All right, so again, here's a graphic. You can see we have a lot of PCs hooked up here. You have server, you have mainframe, and the switching nodes are just what comprise the actual network. So you can see personal computer A, personal computer B, mainframe is C, servers labeled as D, personal computer E, and personal computer F. While personal computer A, you could go through switching node 4 to 7 to 6 to get to F or E, or you could go 4 to 5 to 6, which would be an alternative route. And just remember that the switching nodes are not concerned with the actual content of the data. Their job is just to route the data through them to get it between two stations or two endpoints in the network. Okay. So some key observations of that previous figure: some nodes connect only to other nodes, so 5 and 7 connected only to other nodes in the network, not to any end users or stations. Another nice observation is some nodes connect to one or more stations. So you can see in this case, node 6 connected to station E and F, similar with node 4. Actually, node 4 connected to just the single station, but that's the node 6 would be the good example there of connecting to one or more stations. And the node station links usually are dedicated point-to-point links. And then node-to-node links usually are multiplexed, so they'll typically use something known as frequency division multiplexing, or FDM, or time division multiplexing, which slices by time. So that's known as TDM. And it's not a direct link between every node pair, as you could see. So there were alternative routes that the bits and packets could essentially travel over that network. There's no one right answer. It's a function of a lot of different things of where it would get routed. All right, so what are some techniques used in switched networks? So these two key techniques are really what you're going to see in switch networks. So circuit switching and packet switching. So with circuit switching, the key there is that there's dedicated communications infrastructure between the two stations. So a public telephone network would be a good example of a circuit switching network. Packet switching network, the message is broken into a series of packets, and each node determines the next leg of transmission for each packet. So it's just like what it sounds like. The message is broken up into packets, and then the node determines where it gets routed to. So the phases of circuit switching, so let's hone in a little bit here on circuit switching, is step one is really you got the circuit establishment. So an end-to-end circuit is established through the switching nodes. And this introduces a little bit of overhead up front, but the good news is once the circuit is established, then you can transfer information freely over the network. So information gets transmitted through the network, and data, maybe something like analog voice, digitized voice, or even just binary data. So once the information transfer is complete, there's a circuit disconnect step that is accomplished where the circuit is then terminated, and each node will deallocate dedicated resources. Okay, so circuit switching compared to packet switching is viewed as being a little bit inefficient. The channel capacity is at the upfront circuit establishment step is dedicated for that duration of the connection. So that means that your utilization is not 100%, and there's a delay prior to the signal transfer before the information is actually transmitted. So that establishment step introduces some overhead, so there ends up being some latency or delay. Okay, so once established, the network is transparent to users, meaning information can flow freely back and forth. But again, the main limitation here is that establishment phase of the circuit. The information transmitted is transmitted at a fixed data rate, only with that propagation delay. So there's a propagation delay associated with the information getting from point A to point B, but that's really the only delay that's encountered after the initial establishment. Okay, so the components of the public telecommunications network. So there's the subscribers, there's the subscriber line, the exchanges, and the trunks. So this is some terminology that's specific to public telecommunications, which is worth going over. So subscribers are just devices that attach to the network. Typically, in traditional telecoms, it's going to be a telephone or cell phone or whatever. A subscriber line is a link between subscribers and the network, also called the subscriber loop or local loop. And then exchanges are the switching centers in the network. So a switching center that supports subscribers is an end office, and trunks are the branches between exchanges. Okay, so again, pictorially, you have your end office, it hooks up to the phone, you have your long distance office, and there's switching that takes place between here, another end office, and the digitization back to the cell phone. So this is an example of a circuit switching network. Once again, you have your initial circuit establishment at your end offices, and then your trunk hooks up to your intermediate exchanges. So how does packet switching work? So let's transition now from circuit switching to packet switching. And this is more of a modern technique, more current day. So like more of IP-based network type of terminology and methodology here. So data will be transmitted in blocks called packets. And before sending, the message will be broken down into a series of packets where the typical packet length will be around 1,000 octets or bytes. And the packets consist of a portion of data plus a header that includes control information. So that header has some detail about where the packets might need to go, etc. At each node along the route, the packet will be received, stored briefly, and then passed to the next node. Okay, so here's a pictorial representation. So you have your application data. It's broken up into these packets, and then a header is added with control information. It goes through the packet switching network, which is depicted by a cloud here, and then it goes, from point A to point B. It's essentially. So packet switching advantages. So essentially the line efficiency overall is greater. So many packets over time can dynamically share the same node-to-node link. Packet switching networks can carry out data rate conversion as well. So if there's, let's say link A to B has 100 megabit per second and link B to C, due to some circumstances, has 50 megabits per second, well, those nodes can carry out data rate conversion to route the packets through the network. So two stations with different data rates can exchange information. And unlike circuit switching networks that block calls when traffic is heavy, packet switching still accepts the packets, but increases the delivery delay. So it'll essentially buffer the information and will introduce some latency, but at least the packets get through, rather than in the olden days where we had busy signal, for instance. Priority can also be used, so you can assign priority for certain packets to be more important than others. A great example of this would be like the 911 call. So those packets are tagged to basically have priority over just a regular call being made. So disadvantages of packet switching. So each packet switching node introduces some delay, and the overall packet delay can and the variance can be substantial. So this variability is referred to as jitter, and it's caused by the differing packet sizes and routes taken and the varying delay in the switches. So each packet requires overhead information. So the that little header for the control portion is considered overhead. It's essentially wasted communications. In other words, there's no real data being transmitted there. It's just control information. Okay, where do the big packets have to go? Do they have priority, quality of service, etc.? So it includes destination and sequencing information. And this also, if you're introducing overhead, by definition, you're going to be reducing your communications capacity. So less information is getting through the network because you have to account for that header, that control information. And more processing is required at each node. So there's packet switching networks. There's something referred to as a datagram, and I'll show a pictorial representation here in a minute. But each packet is treated independently without reference to the previous packets, and each node chooses the next node on the packet's path. So the packets don't necessarily follow the same route and may arrive out of sequence, but then the exit node will restore the order of the packets to its proper and original order. And then it's the responsibility of the exit node or the destination to detect the loss of a packet and how you might recover that. So here's kind of a pictorial representation where you have these three packets that need to be transmitted from this workstation over to server. So essentially you have 3, 2, 1 as the order. You can see 3 routes this way, 2 and 1 end up going down here. 3 ends up going down here, over here, 2 gets routed and 1 goes this way, and then essentially they arrive here, and it's the responsibility of the exit node to actually do the reordering. And actually, I might try something real quick just to show you this a little bit better in terms of the sequencing. So here you see the packets go through the nodes, and then 1 gets routed down there, 3 arrives first, and then the exit node has to order them as 3, 2, 1 once again. All right, great. So on to the next. So packet switching network. So the datagram, that picture and basically little vignette I showed you was referred to as a datagram, where the exit node has to do the ordering. So the advantages is that the call setup phase can be avoided, and because it's more primitive, it's more flexible, and the delivery is typically more reliable. Okay, so the packet switching network, another type is the virtual circuit. So there's a pre-planned route that's established before the packets get sent. So it's emulating a circuit switching network. Hopefully you pick up on that, but it's a virtual circuit, so it's still technically packet switching. But the reason it's called virtual circuit is because, like a circuit switching network, which establishes the route beforehand, the virtual circuit of a packet switching network establishes a pre-planned route a priori or before the packets get sent. So all packets between the source and destination will follow this route, and the routing decision is not required by the nodes for each packet, which reduces that overhead at least. And it emulates, as I mentioned, a circuit in a circuit switching network, but is not a true dedicated path. So the packets still get buffered at each node and queued for the output over the line. Another thing is that this can still do data rate conversion. Okay, so just to give you the virtual circuit illustration here, you can see these packets flowing over the virtual circuit path is established as shown here with the dotted line, dotted red line, before any packets get sent. And all packets will just follow the same path, and then the reordering is all the packets automatically arrive in order. So that's a key delineation. The exit node no longer has to do the routing because the packets were sent over the same path, so they're pretty much guaranteed to arrive in the correct order. So that's really the takeaway there. All right, so once again, virtual circuit, well, we have the advantages of that the packets arrive in the original order, the packets arrive correctly, packets are transmitted more rapidly without routing decisions made at each node. So again, the routing decisions made at each node in the previous, like with the datagram, I mean, that introduces overhead and latencies and delays. So the fact that there's a pre-established path in this virtual switching packet switching network reduces some of that overhead. All right, so packet size and its effects on transmission. So breaking up packets does decrease transmission time because transmission is allowed to overlap. So I'll show you this in a little bit, but you have basically your entire message plus header information sent at once, and then that gives you a transmission time of, well, 129 octet times. And then in the second picture, I'll show you the message broken into 2 packets, and then basically plus the header information, and this is done and accomplished in a reduced transmission time of 92 octet times. All right, so this will make more sense when I show you this illustration. Basically, for this illustration, you have time on the vertical axis, and then you have the various nodes that are being transmitted to and from. So X and Y are the end stations, and then A and B are the intermediate nodes. Here's the 1 packet message, and then the amount of time it would take, 2 packet, 5 packet, and 10 packet. So there's something interesting that will happen here. So node X starts sending the packet at time t0, and notice there is the control, the header information shown in blue, and the actual data in the red or the maroon there. So then this packet finishes at time t1, so it then gets routed from X to A, and then it goes from A to B now. Node A now has the full packet. It can start sending the packet at time T1 to node B. So node B starts sending the packet to node Y at time T2. So then node Y finishes receiving the packet at time TS. I mean, this is generalized. So that's the point, is it took a certain amount of time. Now with a 2-packet message, node X splits it into 2 parts, creating 2 packets by adding a header to each. Here, and then here it starts sending the first packet. So packet 1 finishes and node A sends it, and simultaneously node X sends packet 2. So what ends up happening is nodes A and B start sending packets 2 and 1 respectively, and then node B sends packet 2, and then the transmissions occur in parallel. The overall transmission finishes earlier. That's the point there. Now we go to the 5-packet message with every packet has their own control header. And then you can do some similar type of thing. All 3 nodes are sending in parallel, so that's the key thing to note. And then the finish time is even earlier than when it was 2 packets. Now there's the law of diminishing returns here, because when you go to 10 packets, the header size is for the control information is on par with what the actual data size is. So you end up, when this is the case, the finishing time ends up being later than even when it was 5 packets, since the header data takes up too much time. So you got to remember, for each packet, it requires a dedicated header. So if you go split it up too much, you end up losing out on some of those gains, because you add in additional headers for the additional packets. But the point is there's an optimal point, so it's different for every network, but I just wanted to show you this illustration, show you to understand that concept. Fantastic. All right, so this just shows overall longer time for the single, shorter time for the split into 2 packets, even shorter time for the 5-packet, but then even slightly longer for the 10-packet, because you have to add in all that control information. So that's a good summary right there. All right. So as I mentioned, when we broke into 5 packets, it was slightly less than the 2 packets. But then when you went to the smaller packet sizes, broke it up into 10 packets, the transmission time actually increased because of the fixed header that's required for each packet. All right, now we get into quality of service, so QoS for voice, audio, and video traffic. So it's just a requirement for steady delivery and puts in bounds on delay variation, and minimal throughput. Some packet loss is acceptable. So for instance, the quality of service for a voice call, like your Skype call, for instance, would be, one level of quality. The quality of service for a bank wire transfer would have to be a much better quality of service, because if you lose a bit or a packet when you're doing a wire transfer, you don't want to be missing any money in your bank account. I mean, I guess if it happened in your favor, you'd be, happy about that, but technically you don't want bits and packets to be received in error for anything, but in order to get it perfect, there's more resources that need to get expended. So streaming live videos, such as a live sporting event, hey, if you lose a few bits and packets, it's not ideal, but nobody's going to be calling the police. Streaming stored videos, such as YouTube, that uses buffering, well, sometimes you experience buffering. With 5G, there's going to be less and less buffering, because we're coming up with ways that we can meet all the users' needs in the network. But if you've ever streamed video over a 3G, 4G network, you know that sometimes there are things that happen that cause the video to buffer, especially if you're trying to stream 1080p or 4K. All right, so video conferencing, it's interactive and has additional requirements for round trip delay, because if you're talking to somebody across the world, you don't necessarily want it to take 5 to 10 seconds for them to receive your transmission, because by the time they received it, they would already be starting their next sentence. So there are minimal qualities of service for different types of applications. Data traffic requirement. So we shoot for eventual error-free delivery after retransmissions in some cases, and it's more desirable the higher the throughput, because if you make an error on one transmission and it's really high throughput, you could just do a retransmit and then get everything perfectly fine. And this is something you might want to use for the bank account, because if there was an error detected, well, you don't want that error, so you do a retransmit. If it costs you about 10 milliseconds, well, so be it. At least it was received correctly. Elastic just means some variation in throughput is acceptable during the transmission. And the types are interactive and non-interactive. So such transactions or web page interactions are considered interactive types of data traffic, whereas non-interactive, there's background downloads of files or email is technically a non-interactive type of data traffic. All right, provisioning of quality of service. So there's over provisioning, where high data rates and low congestion, basically, in other words, if there's low congestion, in other words, there's tons of bandwidth available, you can give everybody who's on the network high data rates. And there would be no need for prioritization, because the person texting his friend about going to lunch would have plenty of bandwidth, and so would the grandmother who fell and needs to call emergency services. She can get her information through the network no problem, so there's no prioritization necessary in those cases. So all traffic proceeds virtually unimpeded, and it's only practical in wireless systems that have abundant bandwidth, which is the point I was trying to make. Okay. Prioritization without guarantees is another type of provisioning for quality of service. So some packets are marked as higher priority, and this is like the 911 call or the emergency service call. The admission control processes are used to identify users and flows that should receive this priority. Again, emergency services is a great example. And then various markings on the packets are used for different technologies. So like LTE is the one that we'd be more familiar with. WiMAX was a competing technology with LTE that kind of fell to the wayside, but it had different techniques for doing some of these prioritizations of quality service. Prioritization with guarantees are that the packets are actually tracked and then given numerical bounds on performance. So there's admission control is also an important part of this, which we won't get too deep into that, but basically think about the 911 call from the grandmother, and these packets, when these types of calls will be made, would be given priority. Okay, so I have event timing for circuit switching and packet switching. So let me just give you this. I think we have like one or two more charts here, but this is a animation that's worth going over. All right, so virtual circuit packet switching. So essentially what you have here is the call request packet. The call request starts being sent by node 1. So this is node 1, 2, 3, and 4. There's a slight delay. Remember that time is on the vertical axis here. The first bit of the call request arrives after the propagation delay. The call request finishes being sent, and then the call request is fully received at that point in time. There's a slight processing delay, and the call request starts being sent by node 2 to node 3. Similar thing happens from 3 to 4. And then there's a call accept packet or an acknowledgement, which goes from 4 to 3, 3 to 2, 2 to 1, and node 1 starts sending its first packet. So this is just for the call request setup. Then packet 1 gets sent from node 1 to 2, and then from 2 to 3, and then packets 2 and 3 follow a similar process. Okay, So node 4 receives all packets, and then there's an acknowledgement packet. The acknowledgement really occurs at the end, where node 1 receives acknowledgement that the packets were received. Okay. All right, so over to circuit switching over here. So once again, so basically node 1 sends a call request and receives a call accept. So once this is established, it's transparent to the user. So that's why there's no delay on the return side there, because it took a little time to get established, but then there's a seamless transfer. All the user data just gets sent over all in one shot, because this is circuit switching, it's not packet switching, so it just gets sent over. And then you have basically node 1 finishes sending its data, and then the acknowledgement signal or the ACK signal gets sent back to node 1 to denote that the information was received. All right, so then the datagram packet switching, a little different. It has no setup or ACK. Basically, it just sends the data over the network, okay? And the exit node has to do the reordering. Okay, I believe that was it for this chapter. So hopefully you learned something, and have a great day.